hypothesis testing is one crucial element in statistics. So if you want to be proficient in statistics, then you really need to learn hypothesis testing. But the great thing is that you can carry out hypothesis testing in R, because R has a lot of inbuilt functions that enable you to do hypothesis testing. And this is different from Python, because Python is a general purpose language, and because it's general purpose language, then what you're going to have to do is you're going to have to import libraries to do what you need to do, such as you would import NumPy to carry out numerical functions, and then you would import SciPy to carry out scientific functions, and some hypothesis tests in SciPy, and you would import stats models to import statistical functions in Python. So those are the three main libraries that you would use to perform hypothesis tests in Python, but you don't need to do that in R, because R is a statistical programming language written by statisticians that enables you to perform hypothesis tests and other functions using R's inbuilt functionality. So this video is going to focus on hypothesis testing. So hypothesis testing is a fundamental concept in statistics that enables researchers to make inferences about populations based on sample data. It involves formulating a null hypothesis, that's HO, and an alternative hypothesis, that's HA or H1, and then using statistical methods to determine whether the observed data provides sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. So the first thing that we're going to do is I've got 5 practice questions of hypothesis testing. So we're going to go over these 5 practice questions. So number 1, a factory claims the mean weight of its cereal boxes is 500 grams. Collect a sample to check this. So the null hypothesis is 500 grams, and the alternate hypothesis is not 500 grams. So first thing we're going to do when we run this program is we're going to set our seed. And the reason why you set your seed is so every time you run the cell, the variables will be set up to the same values. So that means that every time you run it, you could get the same outcomes theoretically. So you do set.seed brackets 1, and you can put any number that you want in the brackets. And then we're going to define our weights. So weights becomes R norm. R is random, and norm is a normal distribution. Brackets 30, so that means there's going to be 30 samples. Brackets mean equals 495, so that means the mean of the samples is 495 grams. And brackets ST, that's your standard deviation, equals 12. Then we're going to run the test. So we're going to use a t-test. So t.test brackets weights, comma, mu equals 500, because 500 is the weight that this factory claims the cereal boxes are. So now what we're going to do is we're going to visualize the data. So we're going to visualize the data by creating a histogram. So hist bracket weights, comma, breaks equals 10, comma, color equals light blue, comma, main equals distribution of weights with hypothesized versus sample mean, comma, xlab, that's your label for your x-axis, equals weights in grams, comma, border equals white. And then we're going to add a hypothesized mean line. So AB line brackets V equals 500, comma, color equals red, comma, line width equals 3. And then we're going to add a mean line. So AB line, brackets, V equals mean weights, comma, color equals dark green, comma, line width equals 3. And then we're going to add a legend. So legend, brackets, top right, comma, legend equals C. So that means we're creating a vector, brackets, hypothesized mean 500, comma, paste 0, brackets, sample mean, comma, round, brackets, mean, brackets, weights, comma, 1, then comma, brackets, then comma, color equals C, brackets, red, comma, dark green, so you're creating a vector, comma, line width equals 3, comma, DTY equals N. So we're going to print off the t-test. So when you print off the t-test, you see that you have a one sample t-test. So the one sample t-test, what it does is it compares a sample mean to a population mean. So our population mean is 500 and our sample mean is 495. So T equals neg 1.9808, brackets, DF, that's your degrees of freedom, equals 29, and your degrees of freedom are calculated as the number of samples minus 1. Comma, p-value equals 0.05716. So in this instance, your p-value is greater than 0.05. So that means you're going to fail to reject the null hypothesis. Because your p-value is greater than 0.05, you're failing to reject the null hypothesis. And then so you've got a 95% confidence interval being 491 to 500. And then you've got your sample estimates, and the mean of X is 495.9895. So we're going to create the histogram. So you can see the histogram. So you can see the sample mean is 496 and the hypothesized mean is 500 because I wanted to visualize the data. And then we're going to go to sample question number 2. Sample question number 2, compare test scores of students taught with method A and method B. So you're going to have two teaching methods being method A and method B. So your null hypothesis is the method A equals method B, and the alternate hypothesis is method A does not equal method B. And then so we're going to use R to create a hypothesis test on this. And the first thing that we're going to do is we're going to set our seed. So every time we run that cell, the variables are going to be set up to the same values. So set.seed brackets 2. And you can put any number that you want in between the parentheses. So method A becomes R norm. That's randomly sampled normal distribution. Brackets 25 means that there are 25 students. Brackets mean equals 78. So the mean of the scores is 78, comma, ST, that's your standard deviation, equals 8. And method B becomes R norm. That's a randomly selected normal distribution, and brackets 25. So that means you've got 25 scores or 25 students. Brackets mean equals 82 and SD equals 7. So you can see that the mean for method 2 is greater than the mean for method 1, but the standard deviation for method 2 is less than the standard deviation for method 1. So we'll run the test and see what we come up with. So we're going to run a t-test. T-test brackets method A, comma, method B, comma, there, that's variance, dot equals true. And then we're going to visualize the data. So dense A becomes density bracket method A, and dense B becomes density method B. So what you're going to do is you're going to create a density curves for method A and method B. Plot brackets dense A, comma, color equals blue, comma, line width equals 3, comma, main equals density plot method A versus method B. That's your title of the chart. XLab is the label for the x-axis equals score. And then we're going to create another line onto the plot. So lines, bracket, dense B, comma, color equals red, comma, line width equals 3. And then we're going to put a legend on top of the chart. So legend, brackets, top right, comma, legend equals C, brackets, method A, method B. So you created a vector for that, comma, column, color equals C, brackets, blue, comma, red. So you've created a vector for that. Line width equals 3, BTY equals N. So we've run the test, and this is what happens when you get your two sample t-test. So this is a two sample t-test because we're comparing two samples. So you're going to compare method A and method B. Your t is 0.017. Your degree of frequency is 48. So basically what you do is you have the 25 scores, or the 25 elements, 25 elements minus 2. So basically you've got 25 times 2 minus 2. So you've got 25 minus 1 plus 25 minus 1 equals 48. And then you've got your p-value as 0.986. So since your p-value is greater than 0.05, you are going to fail to reject the null hypothesis. And so your confidence interval is neg 4.7 to 4.8. And then your sample estimates, a mean of X is 80.67 and mean of Y is 80.63. And so this is the chart that has been created. So you've got mean A, which is slightly smaller than mean B. So mean B is giving you a higher reading than mean B, but your p-value is still greater than 0.05, so that means you're going to fail to reject the null hypothesis. So now what we're going to do is we're going to go over practice question number 3. So a fitness program measures participants' resting heart rate before and after 8 weeks. So your null hypothesis is before mean equals after mean, and your alternate hypothesis is before mean is not equal to after mean. So we're going to use R's inbuilt programming to generate these hypothesis tests. And so the first thing we're going to do is we're going to generate the data, and we're going to set our seed. And when you set your seed, every time you run the cell, the variables are initialized to the same values. So set.seed bracket 3. And then so we're going to set our values before it becomes our norm. That's randomly selected normal distribution, brackets 20. So you're going to have 20 participants, comma, mean equals 72. So that's their mean heart rate, comma, ST, that's your standard deviation, equals 5. And after becomes before minus our norm, that's randomly selected normal distribution, brackets 20, that's your 20 participants, comma, mean equals 4, comma, ST, that's your standard deviation, equals 2. So we're going to run a paired t-test. So it's t.test brackets before, comma, after, comma, paired equals true. So with the paired t-test, the paired has to be in the true position. If paired isn't true, then what's going to happen is that's going to affect your readings. So you always need to be clear as to whether the samples are related to each other. So if the samples are related to each other, then it would be a paired t-test. But if the samples are not related to each other, then it would be a different type of t-test, such as a independent t-test. So now we're going to visualize the data in a box plot. A box plot brackets before, comma, after, comma, names equals C brackets before, comma, after. So you're creating a vector that says before and after, comma, color equals C brackets sky blue, comma, light green. So you're going to have two colors, being sky blue and light green, comma, name equals before and after paired measurements. That's the title of the graph, and comma, Y lab, that's the label on the y-axis, equals values. And then you're going to add a grid for readability. Grid equal brackets nx equals na brackets ny nx equals na, comma, ny equals null. And then so we're going to get the results of the paired t-test. So the data is going to be before and after. T equals 10.354. DF, that's your degree of freedom. And so that's going to be 19 because it's going to be 20 minus 1. So you've got 20 samples minus 1, and that's your degrees of freedom. P-value equals 2.998 to a negative 9 value. So that means that's a really low value. So it is definitely lower than 0.05. And since it's less than 0.05, you are going to reject the null hypothesis in favor of the alternate hypothesis. And the alternate hypothesis is the true mean difference is not equal to 0. So you have a 95% confidence interval of 3 to 4, and you have your sample estimates. Your mean difference is 4.107. So we create the box plot. So when we created our box plot, you've got two box plots. One box plot is before, and the second box plot is after. And so you can see on the first box plot, on before, I think it's heart rate, isn't it? It's resting heart rate. On the box plot before, the resting heart rate is higher than the resting heart rate of the box plot after. So that means that people's resting heart rate has decreased following an exercise program. And since there is a significant difference between before and after, the null hypothesis is going to be rejected and the alternate hypothesis is going to be accepted. So that means before is not the same as after. So now we're going to look at practice question number 4. So you're going to test whether gender is independent of product preference. So your null hypothesis is gender and preference are independent, and your alternate hypothesis is gender and preference are associated. So we're going to use R to perform this hypothesis test. We're going to create a table. So table becomes matrix brackets C brackets 30, 20, 25, 35. So that's your matrix, which you created a matrix to do that. So in row equals 2, so you're going to have 2 rows, and by row equals a true. So call names of table become product A, comma, product B, and row names of table become C brackets, male, brackets, female. So in the columns, you're going to have column A is going to be product A, column B is going to be product B, and on the rows, row 1 is going to be male, and row 2 is going to be female. And then what you're going to do is you're going to run a chi-square test. So chi-square.test TBL, and so that's going to run the test. And then we're also going to visualize the data. So we're going to visualize the data with a bar plot. So bar plot brackets TBL, comma, beside equals true, comma, color equals C, bracket steel blue, comma, tomato. So that means you're going to create a vector with the 2 colors in it. Name equals product preference by gender. That's the title of the graph. XLab, that's your label on your x-axis, is product. YFab, that's your label on your y-axis, is count. Legend.text equals true. Args, and that means arguments. Dot legend equals list brackets. Title equals gender, comma, X equals top right, comma, BTY equals N. And then so now what we're going to do is we're going to get the results of the chi-square test. So it's going to perform a Pearson's chi-square test with Yates continuity correction. Your data is going to be the table. X squared equals 2.97. DF equals your degree of freedom, and it's 1. And the reason why is because you have 2 rows of data. And then so 2 minus 1 equals 1, so you have 1 degree of freedom. And your p-value is 0.8482. So your p-value is greater than 0.05. So you are going to fail to reject the null hypothesis. And then we print off the chart, the bar chart that we have created. So product by preference by gender. And then so you see product A, the males are higher than the females. And then product B, the females are higher than the males. So next thing we're going to do is we're going to have our last practice question. So we're going to compare the mean plant growth across 3 fertilizer types. So your null hypothesis equals mean 1 equals mean 2 equals mean 3. And your alternate hypothesis is at least 1 mean difference. And we're going to use R to carry out this test. So the first thing that you want to do is you want to generate your data. And then so we're going to set the seed. And so every time you run this cell, the variables are going to be initialized to the same values. So you have set.seed brackets 4. So first one becomes R norm. That's a randomly selected normal distribution, brackets 20. So that means it's 20 elements in the distribution, or 20 samples, comma, mean equals 15, comma, SG, that's your standard deviation, equals 3. And then part 2 becomes R norm, that's your normal distribution, randomly selected, brackets 20, comma, mean equals 18, comma, SD equals 3. And then part 3 becomes R norm, that's a normal distribution with randomly selected, brackets 20, that's 20 elements in the data, comma, mean equals 20, SD, that's your standard deviation, equals 3. So growth becomes, they're going to create a vector for that. Growth equals C brackets vert1, vert2, vert3. And group becomes factor brackets rep, so that means like repeat, brackets C, so that means combine, brackets F1, F2, F3, each equals 20. So you're going to combine that, repeat that 20 times. And then we're going to run an ANOVA. An ANOVA is an analysis of variance. And then what analysis of variance is, you check the means of more than 2 samples of data. And then so since we've got 3 samples of data, it would be appropriate to run an ANOVA on this test. So ANOVA result becomes AOV brackets growth and a squiggly sign group. So basically, and then you're going to have a summary of your ANOVA result. So we're going to visualize the data after we have run the ANOVA. So ANOVA, we're going to create box plots for this. So box plot brackets growth and then a squiggly sign group, color equals C brackets sky blue, light green, salmon. So those are the 3 colors of your 3 box plots you're going to create. Main equals plant growth by fertilizer type, so that's your title. X lab is the label of the x-axis equals fertilizer, Y lab equals growth, and that's the label on your y-axis. Grid brackets NX equals NA, NY equals null. So we're going to get the results of the ANOVA. So the results of the ANOVA are your degrees of freedom, your sum of squares, your mean of squares, your F value, and your PRF. So your group is 2 degrees of freedom, 158.3 sum of squares, 79.19 mean of squares, 10.61 F value, and 0.000121 is your PR is greater than F. And then so your residuals are, the degree of freedom is 57, and so that's 20 minus 1 times 3, so that's going to be 57. And your sum of squares is 4.85.4, and your mean of squares is 7.46. And then you get your significant codes, and it gives you some codes as well. So we have the chart that we have created. So you've got F1, that's fertilizer 1, F2, and F3 being fertilizer 2 and fertilizer 3. And then you've got your growth. And then so it's telling you that fertilizer 3 has the highest growth of fertilizer 1 and fertilizer 2. So it doesn't tell you what the p-value is, but I'm assuming that the p-value is PR brackets greater than F, and it's 0.000121. So I'm assuming that the null hypothesis is going to be rejected in favor of the alternate hypothesis, because at least one mean differs. And you can see from the box plots that we have created that the mean of F1, or definitely the IQ or interquartile range of F1 is about 16. It's above 15. The IQR of F2 is below 20. And the IQR of F3 is slightly above that. So I'm just assuming that this PR brackets greater than F is like a p-value, and it's going to be they're going to reject the null hypothesis in favor of the alternate hypothesis. But what we can do, so you've got 18 and 20, so let's just say 15 and 15. See what happens. And we run it again. So we know that the three means are 15, 18, and 20, but I'm just putting all of them at 15 just to see what happens. And so that's interesting because you've got a mean of 15 on all three and a standard deviation of 3 on all three, and it's still giving you slightly different IQRs, interquartile ranges. So the first interquartile range is below 16. The second interquartile range is around 16. And the third interquartile range is around 15. And you can see that the PR brackets greater than F is 0.374. So what that would tell you would be that the means are very similar. The means are the same. So that means that you would fail to reject the null hypothesis. But let's go over here. Let's just slightly change these. Just very slightly change these. So rather than 15, 18, and 20, we'll make it 15, 16, and 17. And so you can see that there's a very slight difference between the IQRs, or the means, between F1, F2, and F3, but your PR brackets greater than F is 0.55. So I think it would still accept the null hypothesis, or fail to reject the null hypothesis. So basically what we've done is we've covered 5 practice questions with hypothesis testing in R that you can practice on to give you an idea of how to conduct an hypothesis test. And it's really great you're doing it in R, because in R you're using inbuilt programs. You don't have to import any libraries to do it. So that concludes this video. The next video is going to be on a statistical subject. I think we're going to be talking about probabilities. So I hope you decide to watch it.